Okay, this is lecture 46. This is the last lecture of module 5 and the last lecture of this course. So in this lecture, we're going to actually revisit the numerical solution of a stochastic differential equation. And I say revisit because you actually saw the numerical solution of a stochastic differential equation in assignment 1. So we're kind of going back around back to assignment 1, and this actually is going to explain a little bit about where those terms in the code came from. Whereas you only modified them previously, now you get a little bit of glimpse into where they actually come from. Okay, so the computational methods that we talk about here, so this is our stochastic differential equation. Our dx is equal to this mu term dt plus the b term dw. And so for the purposes of a computational method, I'm just going to simply call mu and f and our b at g, just to make explaining it just a little bit easier. So the method that is typically used is what's called the stochastic Euler method or the Euler-Maruyama method. And so this is a method that's kind of based upon ordinary differential equations. It's of order delta t. There is a method which is slightly more accurate, the Mistin's method, which is of order delta t squared, but it doesn't actually improve the accuracy enough in order for people to use that over the Euler, stochastic Euler method. So most of the time people stick with the stochastic Euler method when trying to implement the solution of a stochastic differential equation. Okay, so what is this stochastic Euler method or the Euler-Maruyama method? So it is simply given by the next value of your variable at the next time step is equal to the previous value plus your f evaluated at the previous value times your change in time plus your g evaluated at the previous value times your delta w. So here, just to give you a little bit of terminology, we assume x0 is x at the initial value, and xi's we're approximating, hoping that they'll approximate x of ti, where here I goes through all of our time steps. So our ti is simply given by our I times delta t, where delta t is the total time divided by the number of time steps. So if you remember back to that assignment 1, the number of time steps was a very important thing to consider. And so here you have to make sure you have enough time steps or your delta t is small enough in order to get an accurate solution. And your delta w is simply your w at your t of I plus 1 minus wt of I. Remember we talked about this as the Joyner process, and then this difference is approximately normally distributed with mean 0 and variance delta t. So how do we implement this for actual stochastic differential equations? So this is our example that we derived previously, where we had our simple birth death, and we had this was our mu or our f, and this was our b or our g. Here, so for this problem, the way that we would actually approximate this is we would say our s at the next time step is our s of the previous, plus here we evaluate this at our previous time step times h, where h is given by delta t. And then this term, again, we evaluate that at the previous. And the way that we approximate our delta w is the square root of h, the square root of our delta t, times our eta. And so here this eta is just a normally distributed random number with mean 0. And so typically what we use is rand-in command in MATLAB to do this. Okay, so for systems, it's basically the exact same thing. In here we just add this I term, so the ith variable of our system at the next time step is the ith variable at the previous, plus our function evaluated at the previous, plus all these interacting terms. So for example, this is the example of the predator-prey model, which is from that very first assignment. So the predator-prey model had this form. So if we're going to approximate numerically what this is, we say our x1 at the next time step is our previous x, plus here this was our f, evaluated the previous one, times our h. this is our G here term, and then our delta W or dW1 is approximated by the square root of h times eta. And similarly for this x2 term. Okay, so this was the code we kind of used from assignment 1. So here we had our here's our formula. The code that we had from assignment 1, we basically, this was our F1, this was our F2, and then we had, this was our G1 and this is our G2, and this is where we actually were using the stochastic Euler method. So we had our new value was our previous value plus our h times our f evaluated at the previous value plus this hs times and hs is not here. I haven't written it here, but this hs is the square root of our delta t. And then g1 times our random number. So this was a normally distributed random number. So now just to look back at our two-state problem, so this is the two-state problem that we derived. So here now we have two different states. So our mu vector, so our mu is a vector now, and our v is a matrix. So one way we can do this is we can say our xn plus 1 is our xn plus our mu n h plus our bn wn. Where here basically we can think of these as vectors now, and we can simply say the vector, the new vector, the next time step is the old vector plus our mu's, and then we calculate the square root of this matrix and multiply it by this vector. So we basically do matrix vector multiplication is how we can actually do this. And so you don't have to actually break it up into the individual components. You don't have to multiply this all out ahead of time in order to code it. So in this previous one, it was multiplied out of ahead of time. We thought about this as our F1 or F2, but we really can, if it's easier and simpler, we can actually leave it in this matrix form, and we can just do this matrix multiplication. So we can do the matrix multiplication here. Okay, so this is the end of the semester, and so what you have left is project 3. Project 3 simply involves 3 different models, and of those models, all you're doing is basically the new stuff that you're doing is going to be implementing the stochastic differential equation, so deriving this stochastic differential equation and numerically implementing it, and then simply comparing it to your ODE and to your continuous time Markov chain. So you have project 3 left, which is due December 10th, and then you have the last quiz. And after that, that is the end of the semester. So it's been good being with you this semester, and hopefully you've learned a little bit about continuous time Markov chains, why you might want to add a stochasticity to your models, and how it might actually be useful in something that you might want to model in the future.